Good morning, everyone. Thank you so much for joining us on this third session of 3 or 4 of Plastics 101. I'm joined here by Brian Pelly, who is a technical specialist at Autodesk specializing in mold flow.
Hi, welcome everybody. Welcome. Good morning, Nikhil.
Morning, Brian. Thank you so much for joining us once again. So, if you've missed the last couple of sessions, this does say part 3 or 4. If you have missed the last couple of sessions, just to let you know, they are up on YouTube. Session 1 and 2 will kind of recap that a little bit, but we are trying to build on the previous sessions as well. So we highly encourage you to take a look at the previous 2 sessions as well. Um, you don't have to look at them before you look at this, of course, but they are up there, and you should see a link in the chat window as well, directing you to those previous sessions. Now, coming to this particular session today and why we're here. So, KETIV in general, we're here to be an extended arm of our partners, essentially trying to make them more competitive and more successful through guidance, technology, and through support. And KETIV also happens to be a MoldFlow specialized partner. What that means is that we have been certified by Autodesk to support all of you, to work with all of you and your companies. And as I mentioned, be an extended arm of your engineering teams, your engineering departments, um, and we're able to solve complex injection molding problems using MoldFlow. So as I mentioned, we will be going over a little bit what we did the previous session, but really the last session, um, which was about a month ago, about 4 weeks ago, we talked about the importance of trying to access and start to use simulation early on in your molding process. So how do these early decisions, like geometry and material and gate location, um, help improve the performance and the product quality itself? And how can you use simulation to kind of get ahead of the problems that you might run into? Today we'll talk about, today's going to be an extension of that. Today we will be talking about um, how do you, how best you make these decisions early on, sure, but try and reduce your manual input into it. Try and um, well, I might as well just go ahead and use the word. Try and optimize your product performance, and of course your process. And we'll dive a little deeper into that as we go through this particular session. Now let's start with what is optimization itself. Optimization, essentially, it's a fancy word that gets thrown around quite a bit, but at the end of the day, it's something that we all do in our daily lives, all kinds of things. Essentially, you pick a quantity that you want to measure, you measure it, you understand um, why your entire system is behaving the way you expect it to be, or understand why it's behaving the way it is behaving based on your measurements, and then you figure out ways to improve it, and you keep going back and forth until you're happy with the final result, with the objective really of maximizing the desirable quantities and the desirable characteristics, and minimizing the undesirable characteristics, right? So whether that is, optimizing your own performance as a professional, whether it is, um, I don't know, optimizing your ideal flour water mix for your favorite bread dough, or whether you're actually designing parts, right? Now you
Thanks,
might have.
thanks for that recipe tip too, by the way.
Absolutely. Yeah, I know we've all been baking a lot over the last few weeks, so I'm sure we all have some degree of understanding about bread baking and what bread dough should look like now. So here we go.
And the impact of your weight. So I need to optimize my weight.
Yep, absolutely. So You might have heard, the term shape optimization, topology optimization, geometry optimization. They all pretty much mean the same thing. Essentially, it comes down to taking your CAD geometry and making it, well, better in one way or another, whether that means making it lighter, whether it means stronger, whether it means a combination of the two. They don't necessarily have to be serial or series in that regard. They can work hand in hand, and a lot of times they do, right? So the entire push around lightweighting that you may have been hearing about recently, that all starts from running a simulation like FEA, for example, running a finite element analysis, and then you come up um, with this lighter part design, which sometimes can even actually hold more weight than your original part could, right? So we talked a little bit about generative design last time around. Again, that is a form of optimization. It uses a slightly different technology there, but at the end of the day, it is all optimization. Now, as I mentioned, optimization is fairly manual, right? So you measure a quantity, you understand it, analyze it, and then you improve it. And then you keep going through this process until you're happy. So typically, a manual optimization, we'll talk about this with respect to mold flow now, with respect to injection molding. You're going to run your analysis, um, view your results and everything, and then you say, well, okay, I'm not happy with the weld lines that I see on this, or the fill time on this. So I'm going to add another gate, right? The fill time isn't even, so I'm going to add another gate. Now, if you're going to add another gate, that's going to add another weld line, which is not ideal. And so maybe you want to move those gates around to to locations where the part's not as weak, where it's slightly stronger, it's not going to be taking on as much load, etc. Or maybe you have found a way to run an FEA on this, run simulation, check the quality of the part, and then you're going to keep going back and forth on this process until you're finally happy with the end result, the final quality of your part. Right? And we're all used to doing this in one form or another, whether that's you as a designer sending something over to your analyst getting back to you saying, hey, this part's not good enough. The safety factor is too low, or it doesn't survive a vibration test or something. You as a designer will have to go back, take that information, and put it back into your design. Translate and then put it back into your design one way or another. Um, that now is a process that does exist already. It's done by analysts. It's done by designers. Um, what we're trying to expand on here and talk about here is the need for this, and how quickly and easily and beneficially you can do it early on in the process. Now, another form of optimization is understanding the actual molding window itself. So in this particular example, we see that uh, with the melt temperature being 220 degrees Celsius, you can then identify, well, the 220 degrees Celsius is clearly, as you can see from that slice plot up there, the 2D slice plot, it's within the preferred or the feasible ranges. Um, but typically, for an optimal design, you don't want this to be right on the edge, right? You don't want to ever over design. If you're building a structural component, for example, it doesn't need to be 10 times the weight it's supposed to be, even though that is technically going to be safe. You actually want it to be as close to safe as possible, or beyond safe, but as close to safe as possible. And this is quite similar, right? You don't want the temperature to be running up too high. So you say, well, okay, I'm going to analyze this at 180 degrees Celsius. So at 180 degrees Celsius, it looks like it's just on the edge there. You see there is a portion of it after a certain amount of time that does kind of transition into the non-feasible region. And so we start to look at all these different quality plots at this point, right? So whether that's going to be pressure drop, whether it's going to be shear stress or cooling time or temperature, whatever that may be. Similarly, if you want to look at, say, for 260 Celsius, you've got another, essentially another plot there that says, yeah, beyond a certain point, beyond a certain stage of a certain point in temperature, this is just going to behave the same way. It's all going to be completely either preferred in the preferred or the feasible region. And so at that point, we're probably over designing it, or the temperature is probably too high in this case. Now, once you've struck upon that ideal temperature, let's say 180 degrees Celsius, you can then go in and say, well, what happens at the same temperature if I use a different material, right? And now suddenly we're looking at greater injection time. We're looking at this in more in the not feasible region, until you keep going back and forth this way. Once you have a molding window, you look at similar materials and how they might behave um, with the same temperature range. Now, optimization does come with its own set of guidelines, right? So you do know that with certain, because this has been done so many times and it's been done empirically, you, there are guidelines out there and rules out there that you can follow for parts with complex geometries and complex internal features. This is especially important when you have high volume um, production, because part quality needs to be high and it needs to be uniform. Uniformity is even more important, really, than high part quality, right? And all of these images that you see here are with respect to cooling channels, and we'll talk a lot more about cooling channels going forward, and we'll also understand why.
Yeah, and these last couple of slides, Nikhil, really remind me of the evolution, the steps towards what I sometimes term like avalanche of data. You start off with very little information data, and then you start adding, as you head towards production, more and more details of variables, where some of these routines quite often help assist in optimization with the mass amounts of data as you march toward manufacturing. And this next section, just feed system and gate design, is also another important thing to explore if you look at the functionality of them, developing a mold and process. The feed system and the cooling are quite often overlooked. We tend to use guidelines. We have guidelines in mold flow and guidelines in the industry. And guidelines are kind of like comfort food. It tastes good initially, but it might not be good for you long term. And you might be missing a different cooling approach, a different gating approach that really gets back to what we need to explore for the part functionality, performance, quality criteria, as well as like the individual ingredients going in. For example, material, is that material shear sensitive, or color combination sensitive to shear rate, shear stress? Sometimes you might be over the guideline limit and get away with it. In a lot of cases you are. In some cases you might need to go well below the guideline for shear rate, shear stress to not see cosmetic issues like blush. If you look at just like tunnel gates in this slide here, there's at least a half dozen to a dozen different forms of tunnel gates to explore that some folks actually consider one having advantage over another. And there's some merit to that and data that you can create based on simulation. But this is like just one small function of a mold in process that extends through the process, fill, pack, and into cooling or solidification, that impacts cycle time, part quality, performance.
No, absolutely agree. And it can sometimes be quite intimidating, right? Because you're starting off with so little information that when you have to make all of these considerations, wondering, well, where do I start? So with this is especially true, I think, when your parts themselves are going to be expensive, and when the parts themselves are going to um, require high quality, uniform quality, that sort of thing.
Yeah, absolutely agree. Does it afford the effort of exploration? Can you get away with a guideline with an industrial, or depending on the requirements? Absolutely.
Yep, and we see that a lot. Uh, Users using a specific type of gate design, a specific molding window, whatever it may be, a specific type of part design, even, and it makes sense all per every guideline that's out there. It makes total sense, but their application just happens to be more specific, and it requires a different approach. So it's worth exploring these approaches early on beforehand, even though it can seem a little overwhelming, it can seem a little time consuming. It will, at the end of the entire process, be worth it, and we'll talk about that a little bit. So I did mention expensive designs. Well, what happens when you have expensive design? Expensive designs. Why does a particular mold need a particular design? You look at this one on the screen right now, and it's pretty complex. If you look at the part itself and the cooling channels around it, it is pretty complex. Well, when you think that the part's going to have excessive shrinkage and warpage, or if it's got varying thicknesses, internal features, all that sort of thing, if you can eliminate more operations after this, if you can eliminate waste, then that's a huge win. Now we have been talking a lot about cooling um, and warpage. The reason for that is because mold cooling can usually account for more than two-thirds of the total cycle time in any production of any injection molded parts, right? So improper cooling leads almost always to unpredictable warpage. Warpage is something that you should normally expect, but if it's beyond what you expect, if it's going to be unpredictable, that's when you have waste. That's when you have money being spent on prototypes, on parts that you really don't need to you need to be molding, when instead you could be figuring all this out on the software, on something like Moflow. So with that particular part that we saw previously, we did have some fairly complex cooling cycles, cooling channels in there, and that is that type of cooling is called conformal cooling. Now, what is conformal cooling? You can see the two images on top there. It's essentially a cooling channel, or a set of cooling channels that can conform to the cavities of the mold itself, right? Reason for this is so we've got a uniform temperature, a uniform cooling rate throughout the part itself, and this, of course, gives us better quality, and of course the ability to hopefully completely eliminate secondary and tertiary manufacturing processes. So this same particular part, the designer did a quick cooling, super simplified cooling system, which, as you will see, doesn't really have all that much, or does is not really conducive to uniform cooling because of the complexity in the part and the just the varying thicknesses in the part itself, right? So if we were to test, let's say it gets slightly more complex and you start to use a more complex cooling system, right? So this is more realistic, it's more machined. Essentially, this is like a conformal cooling channel, or set of cooling channel system, but it is still limited by channels actually being machined in, right? So even though this is slightly better than the oversimplified version in the previous slide, this still is not ideal. We still have some irregularities and non-uniformity in the cooling. And really, the way that seems to be best to deal with a part like this is to build conformal cooling channels. Now, if you look at this part itself, it looks quite complex, right? The tubes that you see in there are the cooling channels. You see all those coolant molecules flowing through the channels. It does seem quite complex. So the question is, does it make sense to actually um, machine something like this, a part like this, with these complex features? When does this outweigh the cost of waste? Well, let's take a look at that. So you see here with the three different cooling layouts, the basic cooling, the time for to reach the ejection temperature at the queried specific area was 185 seconds in the first one, in the basic system. The slightly more complex system was almost a twofold improvement on that, right? So it's 100 seconds. Compare that to the conformal results. That same spot now cools in 75 seconds. So you do have right off the bat with your first pass, you have a 25% increase or improvement in the cooling. So is that 25 seconds in cycle time, especially if this is going to be a high volume product, is that going to be more or less beneficial than, say, not using it, right? So if you were to, what is that trade-off going to look like? Is that trade-off worth it? Does it justify the cost of actually building something so complex in terms of the CAD geometry? Well, it probably does. It probably does, especially if you're using this for high volume manufacturing.
Yeah, the other point there is think about if it doesn't, what a lot of money and time spent that could have been avoided if it doesn't make a difference, right?
Exactly. Yeah, absolutely. So, at the end of the day, if you're going to be making these decisions, you've got to consider what the net effect is going to be. If this is going to be one single part, then sure, maybe you can spend the time. If it's going to be a handful of parts, maybe you don't want to be spending as much time and money, machining and remachining and going back and prototyping and all of that stuff. But if you've got to build thousands of parts of these, then yeah, it does absolutely make sense to explore your options beforehand until you find something that it's going to work, and you know that you can be happy uh, with a final part. Now, optimization in Moleflow takes two forms, right? The first one is called parametric optimization, and that focuses almost exclusively on geometric variables. It's essentially an automated way to adjust, your different factors, all your different variables, and run, a series of analysis basically to, without actually changing the original CAD model. So if you want to make changes to, individual parameters, individual molding settings, etc., process settings, then sure, you'll be able to do that. You have to first select your baseline geometry, your, fundamental, your foundation, and then choose the geometric parameters to be changed, right? So, and what you will need to do then is specify a range, an acceptable range for each of these parameters, and then run these analyses, well, hopefully parallelly. Hopefully you're able to do that. Um, Hopefully parallelly, so you get your best combination of results, and you're able to play around with them and visualize the results at every single one of these ranges. Now, this again focuses almost exclusively on the geometry itself. There's another approach which is called design of experiments, and we'll talk a lot more about this. Design of experiments focuses mainly on the process variables and the process settings. So what it does is automatically, with the process settings, you don't really have a baseline. You've got multiple baselines for multiple individual parameters and individual settings. You've got your baseline mold geometry and the part geometry, but all your other characteristics, mold temperature, melt temperature, injection pressure, etc. All of these different criteria can be taken into a consideration for this design of experiments, and you will have ultimately multiple results giving you multiple different quality criteria or multiple different metrics of quality criteria, which you'll ultimately be able to choose from. But the bottom line is here, you're starting from with a design of experiments. I won't say starting from scratch, but you're starting with a lot less information than you did with a parametric optimization, right? Parametric optimization, you're taking existing geometry, putting it in there, and you know that your variation is going to be only within certain ranges. So you're even easily able to uh, verify that quickly. With design of experiments, you are running multiple simulations from multiple variables and ultimately having the software filter that down into some easily readable, acceptable results. Um, and most of the time, it comes down to you as the user to be able to choose from one of them and select what the best um, combination, I suppose, of these variables is going to be. Now, again, when we talk about optimization and mold flow and optimization of your injection molding process, you can optimize this throughout the process, right? You can optimize the fill process, the runner balancing, or the runners. You can optimize the cooling part of it. You can optimize the packing profile, and you can optimize the warpage part of it. Now, the reason, again, we're focusing on the warpage here is because there's usually two main causes of warpage. First one being non-uniform cooling, and the second being inconsistent shrinkage, right? So essentially what we were talking about previously, if your cooling isn't uniform, then that's going to lead to unpredictable warpage. If your shrinkage is not uniform and consistent, that's going to lead to some unpredictable amounts of warpage as well. Now, as you can see here, this is actually you see warpage shows up at the end of this process, at the very end of this process. Now, the reason for that is because it's very difficult to isolate the individual causes of warpage without actually looking at every single aspect that came before it, because warpage is so dependent on the things, on the processes that come before it. They're all so interrelated, so connected. So that's why we're going to be focusing on cooling and warpage the most throughout this particular webinar. But again, that doesn't mean that the other forms of optimization are not useful, because if you're not able to optimize, or if you're trying to optimize the warpage and the cooling, you likely have to look at every other criteria in there as well.
That's a good point. In regards to adding detail, that avalanche of detail I mentioned earlier, if upfront, you certainly can make some assumptions and see geometry effects with, say, ideal cooling, uniform still temperature, but you might miss something. And shrinkage is quite complex through thickness, region to region, and even orientation effects can sometimes be identified early on. But until you expose it to, a bad runner design or an inefficient cooling design, it that upfront work really didn't help if you still made a mistake later on in the phase. So great point on that.
Yep, agreed. Okay. So before we get into the heavy hitting part of this, um, I want to quickly run through parametric optimization, what that looks like. So it gives you an automated way to study and examine changes to, again, the geometry of the part. That's the important part here. The part geometry itself is what parametric optimization deals with. Um, to understand, basically what the impact of every change that you make is to the cycle time. Like that's what it helps you understand. Now, instead of manually adjusting each design variable as we did previously, right, with the example that in the first or the second slide, where you said, yeah, well, the wheel hub that we had, we added gates to it, and then we saw that it added more weld lines, and so you tested that for strength, etc. Here in this case, you make your geometry changes, and instead of manually adjusting the design for every single variable, you can actually automate the analysis by defining a range of values, as we talked about. And for each parameter, you can specify that range and whether it is wall thickness, cooling channel, um, the location of the cooling channels, gate sizes, etc. You will see those individual results, and you will be able to, for example, in this case, we're looking at shrinkage percent, for example, we're looking at the deflection with each single design iteration. So you keep going that way to identify what your best geometry is going to be, and then maybe combine that with the design of experiments to understand what your best process settings are going to be. Now, design of experiments. This really is the big part of this. It's the we have found that a lot of folks are intimidated by design of experiments simply because you start with nothing, you start with very little information, a lot of variables, um, and you come out with a pretty good idea of what you need to do. So that process can seem a little daunting to some if you haven't really explored this. But we're here to show you that this isn't, it's not as crazy as you might think it is. Um, it tends to be fairly intuitive once you start doing it, start getting into it. But basically, what it is it's a statistical method. It uses statistical methods to understand the relationship between different factors that affect a single process, and give you how sensitive each variable is to the process itself, right? So well, that's going to tell you, if it tells you, for example, the melt temperature and the injection pressure are two variables that have the most influence on the final result of part quality, then you know that all you need to focus on is those two variables, right? The other variables, if they're not going to impact it no matter how much you modify them, then you don't really have to focus on optimizing the part or optimizing your process for those variables. You instead just focus on the ones that DOE tells you are important. Now, if you joined us for the previous sessions, you might have seen this slide before. Basically, what we're saying is we're going to identify the independent variables in any process. We're going to select what criteria we want to measure, and then run the design of experiments study. And so the decisions that we can make at the end of that, based on part, for example, will be things like wall thickness, drafts. For the mold, there's going to be gate sizing, number of gates, cooling channels, etc. For the process, melt temperature, packing profile, coolant, cooling time, etc., and also the type of material itself, right? So you can optimize uh, all kinds of metrics, flow front temperature, shear stress, shrinkage, etc. All you need to do is identify what the independent variables are, and DOE allows you to do that. Now, the net effect of all of this, the end result of all of this is you'll see a result with a number of, fancy looking plots, but at the end of the day, what you will see is how important a specific parameter is to achieving a certain result. So as you can see at the bottom left there, mold temperature in this particular case is not all that influential on the final result. What is clearly was clearly more influential are the melt temperature and the flow rate. And so logically, if you were to optimize those two quantities, then you will get better part quality. Now, the image on the right tells you kind of what the difference is between the two approaches, right? One being with upfront simulation and the other being without upfront simulation. So if you're not exploring your design and understanding all the different possibilities with your design, whether that's the process design or the part design or the mold design, or even the material, really, if you're characterizing your own, then sure, your design time is probably going to be, your R&D and design phases are probably going to be shorter, right? In this case, they're saying 4 weeks. Your production time is going to take, well, however long it takes. In this case, it's 37 weeks. With upfront design exploration, you're probably going to have a longer, significantly longer, I would say, R&D and design time, right? In this case, it's 1.5 times what we saw previously. But if at the end of that you're able to shave off several weeks from your production time, in this case they've been able to shave off 6 weeks from the production time, the end result is you're able to save 4 weeks in overall production time, which is great, which is going to be a huge differentiator if you're, with your competition, or just even internally from a purely revenue perspective. That's a huge win, right? So when we say it is worth, more often than not, spending that time up front to analyze all your different options and what your optimal solution might be, this is exactly what we're referring to. Now, in mold flow, again, specific to injection molding, we have, certain quantities we want to measure, right? So for example, let's say we want to measure warpage versus you want to measure melt temperature against warpage, and you see there's a trend forming there. If you want to look at flow rate versus warpage, that doesn't really mean much. If I'm looking at this trying to understand something from here, I'm not understanding all that much from this. So it probably warrants further exploration.
Yeah, it reminds me of that curve too. Reminds me of when you have two people arguing about their experiences. It's quite often depends on what side of the curve they live, and nonlinear relationships like
Yep.
this are very hard to predict.
Yeah, absolutely. Unlike the mold temperature in this case, where again, you see exactly what's happening. You see that there really isn't all that much effect, or all that much effect that mold temperature has on warpage.
It's
So
stop tweaking that knob, please.
yeah, exactly, right? So, what this is going to give you is the ability to solve all of this at the same time. And Brian, feel free to jump in here. It's going to give you that ability to solve all of these and look at all of these.
Yeah, it reminds me of just where I came from, the 1, 2, 3 iterations, and you make your choice. And there's a couple of key benefits that have evolved over time as our optimization routines became more accessible and quicker with the cloud computing capacity that we have today. And that's three major changes to the way I look at problems. One, running a DOE allows us to expose quality criteria to variation, something that we never had time to do before, or a good method to do that. And now we can through DOE. and then get to a ascended process, or help, develop that process early on around quality criteria or things like geometry, like you're going to show next. And then the third, and shouldn't be a surprise, but it is, like where Moldflow users typically start is troubleshooting. And DOEs give you that roadmap, or that treasure chest of key variables and which ones affect what quality criteria. So that ranking of what variable to go to when you start to have quality issues on the manufacturing floor. And those are really three big benefits that we just started to see, I would say early 2000s, 2005, when DOE was already around, but our solving capacity was the missing gap. And along came cloud solving, which changed that game.
Yep. Absolutely. And again, this is it's all well and good, looking at graphs and looking at surface plots and statistical tools, right? Such as statistical results. But what does this actually translate to into an actual part, into an actual injection molded part? Well, essentially, what it translates to is you've got this nice little interface that you can play around with in real time, and as you move the sliders around, you'll see that the weld lines will move, right? The
Here's
you
another
may.
game changer too, applying geometry.
Hmm.
So in this case, the upper left-hand section is a thickness variable acting as a flow leader to drive where you want or don't want your weld
Hmm.
line. And there's examples of that in the parametric optimization too. And one of the distinct game changers for MoldFlow was having geometry now in MoldFlow as a variable for these optimization
Yeah,
routines. Very powerful.
it is absolutely. So it, like I said, it actually helps you translate that statistical information into something that you can look at, something physical, what that actually means for the part and the product itself, the end result. So that's uh,
Exactly. A lot less intimidating than a pile of data.
yeah, exactly. So, well, the question is then, when do you use it? Well, you use it for all molding processes, all analyses types, and all mesh types. That should be enough. But
A lot of options.
yep. But no, honestly, when you would use this when, um, especially your input variables are processing parameters. So
Yeah, I think I've had a couple of, cases where a single variable, a single variant, I just wanted to map out an old classic viscosity study that was being done on the floor. Things like instead of coupling this data, just looking at a Taguchi process to see what are the key variables for this quality attribute I'm going after. So there's a lot of different reasons why I might choose some or the other.
yep, absolutely. And you know, as you mentioned in the previous slide, Brian, the the power to now be able to kind of merge your geometry tools with the DOE results. That's something that is really useful as well. So I mentioned previously that with parametric optimization, you do need a base analysis. Well, there's no reason you wouldn't be able to use both of them, right? There's no reason you wouldn't be able to start with something very abstract, run a parametric optimization, identify what the best geometry is going to be, and then run a DOE after that, identify what the best process for that specific geometry is going to be, and then go back and forth on each optimization routine to really zero in on your best part geometry, your best processing parameters for that specific geometry. So really now you're able to start with pretty much nothing, pretty much just the CAD geometry, and even that doesn't need to be you know completely locked in before you even start optimizing your process for geometry. Anything else to add here, Brian?
No, not particularly. At this moment, I think I've got a couple I'll save to the end.
Okay, well, we are at the end. If there's any
I see a
questions.
lot of hidden slides. Yeah, you're right. Great. So yeah, I would just say, you know, to emphasize the couple key points there with the choices of exploration. Of course, you're not going to do this on every single project, but those that matter will have an impact on what you see as far as key design choices that impact the bottom line. It may be a lot of work up front, but if the project's worth it, we see benefits over and over again using these approaches of exploration and optimization routines as well. And as Nikhil highlighted, design of experiments is really not that difficult to visualize and understand. It's literally 3 clicks and you've got this massive amount of data in the background crunching away, ready to give you visual data that is fairly easy to interpret and point you in the right direction. And again, the use cases that I've seen is just exploring variation. It makes you have better choices. There's no doubt that you can be paralyzed, you know, paralyzation through overanalyzation, but in this case, it's data that can be very concise and get you to the point you want to get to.
Awesome, thanks for that. So yeah, in summary, really what we went over today was we built on what we did the previous 2 sessions, and we talked a little bit about how you would validate your mold design. So we talked about gates, cooling, etc. Talked about process molding windows and what those actually look like and how you would optimize them and simulate them. And we talked about optimization in terms of geometry and in terms of process. So parametric optimization, design of experiments, how the two of them go together and how they work together as well. Now, for the next session, we are going to be focusing exclusively on simulation itself. So the importance of the nature of the inputs into simulation and the results. You know, you may have heard this garbage in, garbage out. So how do you make sure that there's no garbage going in? Well, and how do you ensure that the results that you see actually make sense? So that's what we're going to be talking about next time around. We will also be connecting this a little bit to, well, what do you do after you mold a part and you see that it's going to be warping a certain amount or shrinking a certain amount? What does that do to the actual strength of the part? So we're going to be talking about some of that as well. Now, I saw a couple of you raise your hands throughout the session. If you have any questions now, we'll give you a couple of minutes to type them into either the chat window or the Q&A box. If you look in the chat window, by the way, you should see links to the previous 2 sessions as well. So feel free to post any questions that you may have. And just to let you know, this is going to be up on YouTube as well. Now, while you are filling in some of those questions, I'm going to go ahead and pull up the page where you can find the next session. Okay. So it doesn't look like there are too many questions. So we have one just asking for the previous sessions and subsequent sessions, I suppose. If you look in the chat window, you should see those links as well. You should see them from Jessica. She's on our marketing team, so you should see them posted in those in the chat window. If you don't see it, let me know. If you cannot find it, by the way, you will be able to find them on our YouTube channel. Okay. So hopefully you can all see my screen. This is our advanced manufacturing page, where if you're interested in well, plastics or anything related to plastics, you will be able to find them on one, our advanced manufacturing page, and two, our events page as well. So the next one for Plastics 101 is the 19th of May, right? And you should again see, by the way, in the chat window, a link to our YouTube channel where this is going to be uploaded. This particular session is going to be uploaded. Okay. So if there's no other questions, I think we will wind this up for the day. Thank you all for joining. Stay safe out there, and hope to see you soon on the next session. Thank you all.
Great. Thanks, Nikhil. Thanks
Brian.
everyone. Bye.